G'day chemistry students. In this video we are looking at dot point 6.2.2 and 6. Our focus is on completing some pH calculations which go sort of beyond the scope of our pH equations flowchart that we looked at in the last video. The style of questions that we'll be looking at today require some slightly higher order thinking, require you to engage in some problem solving and plan out your solutions before you actually go about trying to come up with an answer. So generally speaking, these kind of problem solving questions will have multiple steps. You'll still need to follow some of the steps using the flowchart, but usually what we'll find is that in these style of questions, we're using calculations and techniques that we learnt about all the way back in the year 11 part of the course, things like concentration changes, reactions, limiting reagents, stoichiometry, all that sort of stuff, and applying those concepts to then be able to process a calculation and determine a pH or a pOH or something like that at the end. Let's get into it. So for some of the problems that we may encounter, we may be asked to complete a calculation in which we have a solution that has a starting concentration and undergoes some sort of change. These changes a lot of the time would be something like dilution or evaporation. What we'll need to do first is figure out what the starting concentration is, and in particular, either hydrogen ion or hydroxide ion concentration. We could use the stoichiometry of the reaction itself. We may need to use some empirical formula concepts as well to be able to find that concentration. If we're given a p-value, what we may need to do is just convert it to concentration. So concentration is equal to 10 to the negative p-value, whichever one it is. We can then complete a calculation to find the new hydrogen or hydroxide ion concentration based on whatever information we're given about the dilution or evaporation at the beginning of the question. Once we know that new concentration, we can then go back and convert to pH or pOH. In our second style of question, we may be asked to find a resultant pH or pOH of a solution once it's reacted with its counterpart. So if you have an acid, what's the pH once it's reacted with a base? If it's a base, what's the pH if it's reacted with an acid? So to do that, you'll need to understand the stoichiometry of the acids and the bases itself, write out a neutralization equation, make sure it's all balanced, see what ratio they react in. From there, you should be able to figure out the number of moles of hydronium or hydroxide that are present. And so that's effectively going to be a limiting reagent style calculation. Once you know how much acid and base should be reacting together, you should then be able to determine which one's going to get consumed first against those ratios and how much is going to be left over. That leftover concentration is going to be what contributes to the end pH or pOH. So that's calculating the difference between the two values. And following those steps will then enable you with that excess ion concentration to be able to calculate either the pH or pOH, whichever one you're being asked to do. So we've got a few questions set up already to complete as some demonstrations. I'm going to walk you through some of the problem-solving processes that I would take to solve these questions and really break down what I do to interpret a question and come up with a path to get to the solution before even really doing any calculations. But let's get into it. So in this first question, we're being told that we have a 550 ml solution of 1.5 mole hydrochloric and that it's been evaporated until 122 milliliters remain. In particular, the final answer that we need to give is a calculation for the pOH of solution. So the first thing that I want to do is, I guess, just identify the processes that we're going to need to take to be able to get to that pOH value at the end of our calculation. The biggest difference compared to anything that we have done so far with any of these pH style calculations is that there's going to be some additional calculating needing to happen before we actually have a value that we can work with to use our pH flowchart. So our first step is going to require a volumetric calculation. And that will yield us the concentration of the hydrochloric acid once it's been evaporated. And so to be able to complete that volumetric calculation, we need to be taking into account the starting volume and concentration, as well as the final volume as well. Using that kind of information, we can do a simple C1V1 style calculation and determine the evaporated concentration of the hydrochloric acid. If we have the concentration of the hydrochloric acid once evaporated, we can use that data to then determine the concentration of our hydrogen ions. Because it's in 1-to-1 ratio, they should be equivalent, but I'll show working for that. Once we know that information, we should be then able to move into step 3, which is convert to pH, and from there convert to pOH as well. So for step number 1, what I'm going to do first is write 2 equations using our C equals N over V formula. So I'm going to write down that N1 is equal to C1 V1. That's just a rearrangement of the equation, and this will represent the dilute version of the solution, or the initial version of the solution. We then have N2, which is also equal to C2 V2, just another rearrangement, and represents the evaporated solution. Now, an assumption that we should be able to make is that if we have a hydrochloric acid solution and that all that's left the container, the solution itself, is water, then N1 should be equal to N2. We can equate then our dilute formula and our evaporated formula here, and write down instead that we have C1 V1 being equal to C2 V2. This equation should be familiar to you based on the dilutions work that we did in Module 2. This equation is really useful because we have C1 and V1, and we also have V2 in our question. The only unknown that we have currently is the concentration of the evaporated solution, C2 here, which in fact is the thing that we want to be calculating anyway. I'm then going to rearrange for C2 and substitute. So 0.550 times 1.5 all over 0.122, and that is equal to 6.76 moles per liter, and that is our concentration of the hydrochloric acid once it has been evaporated, which is exactly what we wanted to do for step number 1. Step number 2 requires us to look at our concentration of hydrogen ions instead. Now, because the concentration of hydrogen ions to the concentration of hydrochloric ions is going to be 1-to-1, we can say that those concentrations are going to be equal. Therefore, the concentration of the hydrogen ions is equal to 6.76 moles per liter as well. That's step number 2. Looking at step number 3, when we're going from concentration of hydrogen ions to pH and then to pOH after that, what we can do is use our pH equation, which is neg log 10 of our hydrogen ion concentration, so 6.76. That's equal to negative 0.83. We can then take that a step further. We know that the relationship between pH and pOH is that they add up to 14. To rearrange that equation, I could have pOH is equal to 14 minus pH, which is 14 minus negative 0.83. pOH at the end, 14.83. And that is our final value that we were required to calculate within the question there. In our second question, instead of an evaporation, we are going to be calculating for a dilution. We have 25 mils of a 4 molar solution of lithium hydroxide. That's being placed into a 500 ml volumetric flask and diluted. We're being asked to calculate the hydrogen ion concentration of the diluted solution. So again, we're working with a volumetric calculation. That's step number 1. By doing that calculation, we should be able to take the concentration of the original solution and find the concentration of the lithium hydroxide solution when diluted. Step number 2, because we're working with lithium hydroxide in particular, we should be able to quite quickly calculate the hydroxide ion concentration, ensuring that we take into account our ratios in our formula. And then step number 3, we just need to take that hydroxide value and convert that to a concentration of hydrogen ions. So let's run through our 3 steps. Step number 1 is our volumetric calculation. Similar to the reasoning that we used before, C1V1 is equal to C2V2. Essentially, we're assuming that the number of lithium hydroxide particles, the number of moles of lithium hydroxide in both solutions are going to be equivalent at all times. Therefore, if N1 and N2 are the same, C1V1, C2V2 is the same using our C equals N over V formula. So that's V1, C1, and V2. We're calculating for C2, which is our lithium hydroxide concentration when diluted. So solving for C2, just going to write that down. And substituting, I've got 4 times 0.025 all over 0.500. That is equal to 0.2 moles per litre. In step number 2, we're going to convert our concentration of lithium hydroxide when dilute to a concentration of hydroxide. So in this conversion, what we need to be taking into account are the ratios of hydroxide to lithium hydroxide. It's 1 to 1. So we can say that the concentration of lithium hydroxide is equal to the concentration of hydroxide ions, both of which are 0.2 moles per litre. Step number 3, we then take this value, and to get from hydroxide ion concentration to hydrogen ion concentration, which is the goal of this question, what I want to be using is our Kw value. So in our data sheet, we know that Kw, the self-ionization constant for water, is equal to 1.0 times 10 to the neg 14. And that is equal to hydroxide ion concentration times the hydrogen ion concentration. Rearranging for hydrogen ion concentration, which is what we want to solve for, we find that that is equal to 10 to the power of neg 14 all over 0.2. And that when we do that calculation, we find that that is equal to 5 times 10 to the neg 14 moles per litre. And that's our concentration for our hydrogen ions. Now, for the last question in this video, we have a slightly different problem to solve. We have a neutralization reaction. We have 12 mils of 3.4 molar sulfuric acid solution being combined with 20 mils of 1.65 molar sodium hydroxide solution. We need to be calculating the pH of the resultant mixture. Now, the pH of the resultant mixture is going to depend on whether or not there is an excess of hydrogen or hydroxide. Whatever that excess is, we can then start to do our pH flowchart style calculations to eventually get to our pH value. So step number 1 is actually going to be some sort of a limiting reagent process. We're going to have to determine what the limiting reagent is. That's going to be step number 1. We're then, with that limiting reagent, going to have to determine, well, how many moles of excess is there after this neutralization reaction is complete, whether or not that's excess of hydrogen ions or hydroxide ions. From there, we can then find the concentration of the excess ion. And that could be hydrogen or hydroxide, completely depending on whether or not the hydrogen or the hydroxide is going to end up being the one that is in excess. Once we have that concentration, step 2 is going to require us to convert to pH. So either we have the hydroxide ion concentration, we get POH and convert that to pH, or we have the hydrogen ion concentration and we convert directly to pH, either or. So for step number 1, what I'm going to be doing first is writing up the neutralization reaction equation for this process. So we have our sulfuric acid reacting with sodium hydroxide, forming sodium sulfate. Note as well that that's Na2SO4 because the sodium has a charge of 1, the sulfate has a charge of -2. And we're also going to be forming water as an additional product. That comes from the neutralization general equation that we've seen before, our salt and water as our products. What we should notice immediately is that these equations are not balanced. In particular, the sodium is unbalanced. So I'm going to be accounting for that first. We should then see that the sulfate ions are balanced, that the oxygen itself is not balanced, neither is the amount of hydrogen present. In fact, we need to double the amount of water on the right-hand side to balance all the reactants on the left. What I then want to begin looking at is how much sulfuric acid and how much sodium hydroxide was present to begin with and available to react. Once we know that kind of information, we can then start to look at excess concepts. So number of moles of sulfuric acid is going to be equal to CV, the concentration of the acid at the beginning, times the volume of the acid. That's these values up here. So 3.4 times 0.012, and that is equal to 0.0408 moles of sulfuric acid present to begin with. For the sodium hydroxide, same thing. It's going to be equal to C times V. That is these values here. So 1.65 times 0.020, and that is equal to 0.033 moles of sodium hydroxide available to react at the beginning. What I then want to compare is the amount of hydrogen that's available versus the amount of hydroxide that's available. And that's because at the end of the day, the reaction that we're really seeing is hydrogen, which is coming from the sulfuric acid, hydroxide coming from the sodium hydroxide, reacting together to form water. The hydrogen and hydroxide essentially need to be reacting in that 1-to-1 ratio. So the next step that I'll be doing is calculating the number of moles of hydrogen. And that's going to be equal to double the amount of sulfuric acid present, which is 2 times 0.0408. And that is equal to 0.0816 moles. And that value there is a lot more useful when trying to figure out what the limiting reagent is and what excess there will be at the end. On the flip side, the number of moles of hydroxide ions is going to be the same as the number of moles of sodium hydroxide ions, because the hydroxide and the sodium hydroxide exist in a 1-to-1 ratio by its formula. So we can just say that that remains as 0.033 moles. So when we make a comparison between these two values, what we should see is that there is an excess of hydrogen ions, and that the hydroxide ions are the limiting reagent. So the question becomes, how much excess do we have? And that's just a simple subtraction. Essentially, if 0.033 moles of hydroxide are going to react with all of the hydrogen ions that are there, 0.033 moles of hydrogen ions are going to be consumed as a result. So the number of moles of hydrogen ions in excess is going to be equal to 0.0816 minus 0.033. That is equal to 0.0486 moles. And we can take this value forward to determine excess ion concentration and then on to our pH conversion. So the concentration of hydrogen ions in our N solution, once neutralization has happened, is equal to N over V. The one thing that we need to be keeping in mind for, and this can be a bit of a pitfall for a question like this, is the V value itself, because the volume of our overall solution needs to take into account the solvents of both of those original acids and bases. So the total volume for this solution is not 12, it's not 20, it's actually 32 mils. So in this V part here, I need to substitute that in accordingly. Otherwise, we're going to end up with a wrong answer. Number of moles is, as we see it up the top, our excess. 0.0486 moles. When we put that into our calculator, we should end up with 1.5 moles per litre. We now can step into our final part here using the flowchart, step 2. And that's just a conversion to pH. So pH is equal to neg log base 10 of our hydrogen ion concentration, so 1.5. And that is equal to negative 0.18. And that is our pH and our final problem solved. And there you go, 3 different kinds of problem-solving style questions that do involve our pH calculations and our flowchart. We saw the impact that evaporation had on pH and the kind of calculations that you need to do at the beginning with those volumetric concepts. Very similar, same kind of idea with our dilutions. And then we used a limiting reagent process to calculate the remaining ions when there was excess acid present in that neutralization reaction and expressing that value as a pH. Thank you very much, everyone. In the next video, we're going to take a slight detour away from some of the many calculations that we find in Module 6. Quick break, we'll be looking at some acid-base techniques and some of their applications. This is going to give us a lot of setup moving forward into the remaining sections of this module. But until then, have a good one.